There's a 60-minute window every single morning that most people sleep through, rush through, or scroll through without a second thought. And according to a growing stack of research in circadian biology and metabolism, that window may be doing more to shape your belly fat than anything you eat at lunch. 3 specific habits, all happening before most people finish their first cup of coffee, keep showing up across independent studies as connected to how the body handles abdominal fat over time. One of them, when researchers tested it over 6 full weeks instead of just a few days, produced a result almost nobody expected. We're getting to that one in just a few minutes, and once you hear it, it'll change how you think about the other 2 habits in this video. Most people picture fat as something passive, tissue that just sits there until you burn enough calories to shrink it. But visceral fat, the kind that wraps around your abdominal organs, runs on its own internal clock. Research published by Joseph Bass and Joseph Takahashi in the journal Science in the year 2010 established that nearly every tissue in the human body, including adipose tissue, contains its own set of molecular clock genes. These genes don't just tell time passively. They actively control when fat cells store energy and when they release it, on a rhythm that repeats roughly every 24 hours. This means your fat tissue behaves differently depending on the hour, independent of when you last ate. In the early morning hours, the clock genes inside adipocytes shift the tissue toward a state that favors releasing stored fatty acids rather than accumulating new ones. Later in the day, especially in the evening, that same tissue shifts toward storage mode. This isn't a minor biological footnote. It's one of the reasons identical meals can produce different metabolic responses depending on what time they're eaten. What makes this relevant to your morning routine specifically is that this internal fat tissue clock doesn't run on its own schedule forever. It needs to be reset daily by external cues. And the strongest of those cues, light, movement, and the timing of your first meal, all arrive within the first hour or 2 after you wake up. Miss that resetting window consistently, and the clock inside your fat tissue can drift out of sync with the rest of your body, a state researchers call circadian misalignment. That drift is where this story really begins. Before you've even opened your eyes fully, your body has already started a hormonal process that most people have never heard of. It's called the cortisol awakening response, and it was first systematically studied by Angela Clough and colleagues, whose 2010 review in Neuroscience and Biobehavioral Reviews remains one of the most cited papers on the subject. Within the first 30 to 45 minutes after waking, cortisol levels rise sharply, not because you're stressed, but because this specific surge is a normal, healthy part of transitioning from sleep to wakefulness. This isn't the same cortisol people associate with chronic stress and stubborn belly fat. The awakening surge is short, sharp, and functional. It mobilizes glucose and fatty acids into your bloodstream, essentially giving your body a burst of available fuel to meet the physical and cognitive demands of the day ahead. Researchers in this field describe this as an allostatic boost, a deliberate biological preparation, not a malfunction. The size and timing of this surge is also directly influenced by light exposure immediately after waking, which is a detail that becomes important later in this video. Here's what most people miss entirely. This first-hour hormonal window is also when your body is most receptive to external timing cues. It's the moment your internal clocks, the ones controlling fat tissue, liver metabolism, and appetite hormones, are listening closest for instructions about what kind of day is coming. What you do with light, movement, and food during this specific window sends signals that ripple through your metabolism for the following 12 to 16 hours. That's the biological stage the next 3 habits are about to walk onto. The first habit researchers have studied involves something deceptively simple: pushing the first meal of the day slightly later, extending the natural overnight fast by a few additional hours into the morning rather than breaking it the moment you wake up. This isn't about skipping meals altogether. It's about the length of the gap between your last bite the night before and your first bite the next day. To understand why this matters, you have to look at what's already happening in your body by the time morning arrives. After roughly 8 to 10 hours without food, liver glycogen stores are already partially depleted from an overnight fast most people experience without realizing it. A 2023 randomized crossover trial following healthy lean males through an extended fasting protocol, published in the journal Clinical Nutrition, found that fat oxidation rises progressively the longer the fasting window continues, climbing steadily hour by hour rather than switching on abruptly at any single point. That detail matters because it means your body is already primed toward fat-burning metabolism first thing in the morning, purely as a consequence of the hours you spent asleep. Extending that window even modestly, rather than immediately reversing it with food the second you're conscious, is the mechanism researchers have been testing directly. What they found when they measured it precisely, including some genuinely surprising longer-term results, is where the real story of this first habit unfolds. The most detailed investigation into this exact question came from James Betts and colleagues at the University of Bath, whose 2014 randomized controlled trial, published in the American Journal of Clinical Nutrition, became known as the Bath Breakfast Project. Lean adult participants were assigned to either consume at least 700 calories before 11 in the morning or eat nothing until noon. Researchers then measured their substrate use directly, meaning they tracked in real time whether the body was burning fat or carbohydrate for fuel. The initial substrate tracking data lined up with what the fasting mechanism from the previous section would predict. Extending the fast measurably shifted the body toward fat oxidation in the hours before noon. But here's the part of the story that most videos on this topic leave out entirely, and it's the reason this habit deserves a more careful look than a simple headline suggests. When Javier Gonzalez and the same Bath research group followed lean and obese adults for 6 full weeks, not just a single morning, and published their molecular findings in the Journal of Physiology in 2017, they found something unexpected. In lean individuals specifically, extended morning fasting was associated with reduced insulin sensitivity in the fat tissue directly beneath the skin, a pattern that did not appear in the obese participants. Short-term fuel switching and long-term tissue adaptation, it turns out, are two different stories. And the second one depends heavily on who's doing the fasting. The second habit has nothing to do with food at all. It's about when your eyes first encounter bright light each day. Catherine Reed and colleagues at Northwestern University, in a 2014 study published in PLOS 1, tracked light exposure patterns and body mass index in 54 adults over a full week using wrist-worn sensors. People whose main exposure to moderately bright light occurred earlier in the day had, on average, a lower body mass index than those whose brightest light exposure came later, a relationship the researchers found held true independent of physical activity, calorie intake, sleep timing, and age. Because this was an observational study, it points to an association rather than proof that morning light directly causes lower body fat, but the pattern was strong enough that the research team described light timing as a potentially modifiable factor worth taking seriously. To understand why timing specifically might matter, a follow-up controlled study from the same Northwestern group, led by Ivy Chung and published in PLOS 1 in 2016, brought 19 healthy adults into a 4-day inpatient protocol under tightly controlled lighting. Participants received 3 hours of blue-enriched light either shortly after waking or later in the evening, and researchers measured the resulting shifts in metabolic function directly. This design allowed the team to isolate the effect of light timing itself, separate from all the lifestyle factors that usually complicate this kind of research in the real world. Quick gut check before habit 3. The cortisol surge, the fat tissue clock, the light exposure timing. None of that is something you can feel happening. Comment the one detail from this video so far that you had genuinely no idea was going on inside your body every single morning. That list tells me exactly where to go deeper next time. The pathway connecting light to your fat tissue runs through a surprisingly direct route. Specialized cells in your retina, distinct from the ones responsible for actual vision, feed information straight to the suprachiasmatic nucleus, the brain's master clock discussed earlier. Angela Clow's research on the cortisol awakening response noted a consistent pattern across studies. The magnitude of that morning cortisol surge correlates with how much light a person is exposed to around the time of waking. Brighter, earlier light doesn't just wake you up faster. It appears to shape the strength of one of the very first hormonal signals your body sends out each day. But the full picture here is more layered than a simple morning light equals better metabolism, headline would suggest. And it's worth being precise about what the research actually shows. In the controlled study by Ivy Chung and colleagues referenced earlier, both morning and evening blue-enriched light exposure increased markers of insulin resistance compared to dim lighting, meaning bright light itself, regardless of timing, produced some acute metabolic disruption. What separated the two groups was that evening exposure additionally produced a significantly higher glucose peak, something the morning group didn't show. In other words, timing didn't eliminate the effect of bright light. It changed how well the body recovered from it. The third habit shifts focus away from light and food timing entirely, and toward when physical movement happens relative to that first meal. Specifically, researchers have studied what changes when moderate movement, walking, cycling, or other aerobic activity, takes place before eating anything, while the body is still in the fasted state carried over from sleep, rather than after breakfast has already been consumed. The biological backdrop for this habit was actually laid out earlier in this video without being named directly. By the time most people wake up, liver glycogen is already partially depleted from the overnight fast, and cortisol is rising as part of the awakening response, both conditions that favor the release of fatty acids from storage rather than their accumulation. Layering movement on top of that specific hormonal window is different, physiologically, than performing the same movement 2 hours after a carbohydrate-containing breakfast has already triggered an insulin response, since insulin actively suppresses the enzyme responsible for releasing fat from adipose tissue. The clearest evidence on this question comes from Alexandra Vieira and colleagues, whose 2016 meta-analysis in the British Journal of Nutrition pulled 27 separate trials involving 273 participants performing aerobic exercise in either a fasted or fed state. The finding was consistent across the pooled data. Fat oxidation during the exercise session itself was measurably higher in the fasted condition. Mechanistically, this tracks directly with what was just described. Lower circulating insulin and elevated catecholamines during fasted movement both favor mobilizing fatty acids as fuel over burning glucose. Here's the honest complication. Brad Schoenfeld and colleagues ran a 4-week randomized controlled trial published in the Journal of the International Society of Sports Nutrition in 2014, comparing 20 young women performing matched aerobic training either fasted or fed, with both groups following an identical calorie-controlled diet. Despite the fasted group burning measurably more fat during each individual workout, there was no significant difference in total fat mass loss between the two groups by the end of the 4 weeks. The acute session-by-session advantage didn't translate into a bigger real-world result once the full month was measured. James Frampton and colleagues, in a 2022 network meta-analysis, published in the International Journal of Obesity, offer a plausible explanation for that gap. Their pooled data showed that fasted exercise without a follow-up meal does produce a short-term reduction in calorie intake, but it simultaneously lowers post-exercise energy expenditure and raises subjective hunger in the hours afterward. The body appears to partially compensate for the fasted training fat oxidation advantage through these downstream adjustments, which helps explain why the acute physiological effect and the eventual body composition outcome don't always move in lockstep. The most directly relevant human data on visceral fat specifically comes from Limin Zhang and colleagues, whose randomized controlled trial in the journal iScience in 2022 compared an early 6-hour eating window against a later 6-hour window and a control group over 8 weeks. Both time-restricted groups showed a significantly greater reduction in visceral fat area, measured directly rather than estimated, compared to participants eating without restriction. A separate 6-week trial led by Przemysław Domaszewski, published in Experimental Gerontology in 2023, followed 116 adults between the ages of 65 and 74 through a 16-hour daily fasting window, eating only between noon and 8 in the evening, which mirrors the delayed first meal habit described earlier in this video. That trial documented significant reductions in body weight alongside measurable visceral fat changes over the 6-week period. In an age group not typically included in this kind of research, it's worth being precise about what these numbers do and don't tell us. Neither of these trials tested all 3 habits from this video together as a single combined protocol, and neither ran for exactly 30 days, 6 weeks, and 8 weeks respectively. What exists in the literature right now is several separate converging lines of evidence, each pointing toward measurable visceral fat changes on a timeline of roughly 1 to 2 months, rather than a single study confirming this exact 3-habit combination produces a specific result in exactly 30 days. That distinction matters if you want to understand what the science actually supports versus what a compelling narrative might imply. The first habit-canceling pattern connects directly back to the light research discussed earlier. Getting bright morning light while also spending the evening under equally bright indoor lighting or screens works against the very signal morning light is meant to send. Since Chung's data showed evening blue-enriched light produced the larger glucose disruption of the 2 conditions tested, pairing a strong morning light signal with an equally strong evening. One creates competing instructions rather than a single, reinforcing one. The second pattern shows up around consistency rather than any single day's choices. Both the Zhang and Domaszewski trials that documented visceral fat reductions used a fixed daily eating window that participants followed every day for the full study period, with compliance data collected and tracked throughout. Neither trial tested what happens when the fasting window shifts unpredictably from day to day. First meal at 8 one morning, noon the next, 3 in the afternoon after that. While no controlled trial has isolated that specific variable, the design of every successful trial in this area shares the same feature: a fixed, repeatable schedule, which suggests predictability itself may be doing meaningful work. The third pattern circles back to the compensatory eating mechanism from the previous section. A related study on fasted evening exercise, published in the International Journal of Sport Nutrition and Exercise Metabolism, found that the reduction in net energy intake from fasted training was almost entirely offset by increased eating afterward. And this compensatory effect was driven overwhelmingly by male participants, with little to no equivalent compensation observed in females. Fasted movement doesn't automatically create a calorie deficit on its own. What happens at the next meal determines whether that morning's physiological advantage actually holds up by the end of the day. Looking across the trials that documented actual visceral fat reductions, a clear pattern emerges around timing. Meaningful, measurable changes showed up at the 6-week mark in the Domaszewski trial, and the 8-week mark in the Zhang trial, not within the first few days, and not from a single morning of doing everything right. This lines up with the 30-day framing running through this entire video. These are habits that require sustained, weeks-long repetition before their cumulative effect becomes something a scan or a measuring tape can actually detect. What none of these trials directly measured is what happens after the study period ends and participants return to their previous habits. The research documented outcomes during active adherence to a fixed protocol. It didn't follow participants for months afterward to see how quickly visceral fat area drifted back toward baseline once the fasting window, the light exposure pattern, or the fasted movement habit stopped. That's an honest gap in what's currently known, not a detail to gloss over. What ties every study in this video together, from the circadian clock research to the light exposure trials to the fasted exercise data, is that timing consistently mattered as much as the individual action itself. Not one of these mechanisms works in isolation, and not one of them appears to work instantly. 30 days isn't a magic number pulled from nowhere. It's roughly the point where several independent lines of research start showing measurable change, provided the underlying habit was actually repeated day after day, without much deviation. If this video helped you understand what's actually happening in your body every morning, hit the like button. It makes a real difference in helping this kind of research-backed content reach more people. Subscribe if you want more videos that go straight to the science instead of the shortcuts. And share this with someone who's been chasing quick fixes for belly fat without realizing the answer might already be built into their morning routine.